Hello everyone. So in today's video we are going to go over this paper titled Don't Take It Literally, an Edit-Invariant Sequence Loss for Text Generation. This paper is still in preprint and is under review. The authors are Guangwei Liu, Zhishao Yang, Tianhua Tao, Xiaodan Liang, Zhen Li, Bowen Zhou, Zhuang Sui and Ziting Ho. And they are from the Chinese University of Hong Kong, Zhenshan, Carnegie Mellon, Tsinghua University, Sun Yat-sen University, JD AI Research, and UC San Diego. I'm really sorry if I mispronounced any of those names. So, as you can see, this paper is pretty recent. The current version of archive is from 6th October. So let's just delve right into it. So neural text generation models are typically trained by maximizing log likelihood with the sequence cross entropy loss, which encourages an exact token by token match between a target sentence with a generated sentence. We've all seen this. Such training objective is suboptimal when the target sequence is not perfect. Example, when the target sequence is corrupted with noises, or when only weak sequence supervision is available. So to address this challenge, we propose a novel edit-invariant sequence loss (EISL), which computes the matching loss of a target n-gram with all n-grams in the generated sequence. Drawing inspiration from the classical convolutional networks, which are convnets, which capture shift invariance in image modeling, EISL is designed to be robust to shift of n-grams to tolerate various noises and edits in the target sequence. Moreover, the EISL computation is essentially a convolution operation with target n-grams as kernels, which is easy to implement and efficient to compute with existing libraries. To demonstrate the effectiveness of EISL, we conduct experiments on a wide range of tasks, including machine translation with noisy target sequences, unsupervised text style transfer with only weak training signals, and non-autoregressive generation with non-predefined generation order. Experimental results show our method significantly outperforms the common cross-entropy loss and other strong baselines on all the tasks. So uh, basically, we'll understand more as we go deeper into text, I believe, because even I haven't read this paper before. But the abstract was what really caught my attention, and it was shared with me. Uh, so I really wanted to read this one up, and this part makes sense intuitively because to maximize the lock likelihood, the more tokens you predict correctly, the more likely you'll maximize the log likelihood. Then you have the problem where the target sequence is not perfect. So there you don't really want to maximize just the tokens because then your accuracy will suffer, I guess. So or even when you have weak sequence supervision, so even in that case, and so that is why they propose this one a mechanism. Convolutional nets, if you're familiar with ImageNet papers, and you must have heard about AlexNet, VHG and all, which are all convnets essentially. And convnets capture location invariance, which I guess they've shown in this example here. So when they describe the image, I'll sort of try to explain what that stuff is. And they've said that since convnets are used extensively, their implementations are also readily available in libraries. So an introduction first. Neural text generation models have ubiquitous applications in NLP, including machine translation, summarization, dialogue system, etc. They are typically trained by maximizing the log likelihood of the output sequence, conditioning on the inputs with the cross entropy loss. The cross entropy loss can be easily factored into individual loss terms and can be optimized efficiently with stochastic gradient descent. You've all seen probably the cross entropy loss numerous times now. Due to its computational efficiency and ease to implement, the training paradigm has played an important role in building successful large text generation models. So, in the Radford et al. Is, I think, the GPT model. Lewis et al. I'm not sure. Is it the BART model? Let's have a look. BART, right? And we all uh, the Radford et al. Paper is the GPT paper here, language from OpenAI. So I believe this is GPT-2, if I'm not wrong. Right. So, however, the A cross entropy loss minimizes the negative log likelihood of only the reference output sentence, while all the other sequences are equally penalized through normalization. This is over restrictive since for a given reference target sentence, many possible paraphrases are semantically close, so even minor variations will be penalized, hence should not be completely treated as negative samples. For example, as shown in figure 1, a cat is on the red blanket should be equally treated with on the red blanket there is a cat. A model trained with cross entropy loss fails short on modeling such type of invariance for text. So you have a cat is on the red blanket, and on the red blanket there is a cat. So you can see essentially this entire phrase has moved here, and the location has changed, but the meaning is same. And a cat is on the red blanket, a cat is on the red blanket. So you can see there is some additional noise in this case. Invariants exist in both images. Image is invariant to translation and text is robust to many forms of edit. So what they're trying to say is, even like this is some sort of a translation, because you've moved this phrase and modified, edited a text, but still the meaning remains the same. Similarly, maybe there's a cat in a field, and the cat is in one frame in the top right corner, and in another frame it's in the top left corner, but both of them should have the same meaning, essentially that the cat is in the field. So there should be location invariance which is being described. All right. Uh, the problem is even more exaggerated when the supervision from target sequence is not perfect. So on one hand, there could be noise in the reference sequence which makes itself not a valid sentence. As in the example shown in figure 1, there is a repetition error in the target sequence which is common in human generated text. So you often write the same word twice, right? With the cross entropy loss, the model is forced to copy all tokens including the error. So if your original data has is twice, then the model will penalize the output of the your cross entropy loss will penalize the output of the model even if it was correct. It had a single is. So with this model is forced to copy all tokens including the error and assign a high loss for the grammatically correct sequence. The exact tokens matching renders the cross entropy loss sensitive to noise in the target, as shown in figure 2. We'll have a look at it. On the other hand, there are many problems with only weak supervision for target sequences. So for example, in tasks of unsupervised text style transfer aiming to rewrite a sentence from one style to another, the original sentence offers weak supervision for the content rather than the style. Yet using the cross entropy loss here is problematic since it encourages the model to copy every original token and thus fail the style transfer. So basically what they're saying is, we've had a look at unsupervised textile transfer problems before. It basically aims to retain the content while transferring the style. So if you have a positive sentiment and a negative sentiment, but you have the same content in both of them, then the problem would be somewhat to keep the content of the positive sentiment sentence and transfer it to a negative sentiment sentence. So for example, in tasks of they've mentioned that, and so cross entropy loss here is problematic because cross entropy loss rewards the model for having similar tokens as the original sentence. So it would encourage the model to copy the original tokens, and then it wouldn't essentially be fair to a style transfer problem, because style transfer might often require you needing to use would often require that you need to use synonyms of some words which would be penalized by the model. So if the model penalizes that, then if the loss penalizes that, then the model would not try to learn it. So here we have sensitivity of cross entropy and EISL loss with respect to different type of text edits. As the amount of edits increases, we use the fixed machine translation model, synthesize different types of edits on the target text, and measure the cross entropy and EISL losses respectively. The edit types including shuffle, changing the word order, repetition, words are repeated, and word blank, words being replaced with a special blank token. Alright, the cross entropy loss tends to increase dramatically once a small amount of edits is applied. In contrast, our EISL loss uh, increases much slowly. So yeah, you can clearly see the cross entropy loss is way higher as soon as the edits start to grow. So this basically means if you have the sentence a cat is on the red blanket and the sentence on the red blanket there is a cat, the cross entropy loss would be much higher as compared to the EISL loss, since there are lots of edits. You've shuffled the words. Alright. So prior works have tried to address this problem using reinforcement learning. For example, policy gradient was used to optimize sequence rewards such as Bloom metric. Such algorithms assign high rewards to sequence that are close to the target sentence. Though it is a valid objective to optimize. Policy optimization faces significant challenges in practice. Though the high variance of gradient estimate makes the training extremely difficult, and almost all previous attempts rely on fine-tuning from models trained with cross-entropy loss, often with unclear improvement. So basically, what they're saying is reinforcement learning settings have been used. Uh, so one of them was to reward with the blue metric. So if the model performed well according to the blue metric, then it would reward them, I guess. So this means essentially the blue metric in some sense looks at overlappings. So if it is close to the target sentence, then the reward would be more. So even though it is a valid objective to optimize, it brings about problems because you have high variance of gradient estimate in this type of setting, so which makes the training extremely difficult because your gradients would not be stable. And almost all previous attempts in this setting have been relying on fine tuning with the cross entropy loss. So they're saying that in this paper they I guess they had not given good ablation studies to indicate why that is needed, because the improvement is unclear. Alright, so in this paper we propose an alternative loss to overcome the weakness of cross entropy loss but reverse all nice properties such as being end-to-end differentiable, easy to implement and efficient to compute, which hence can be used as a drop-in replacement or combined with cross entropy. The loss is based on the observation that a viable candidate sequence shares many subsequences with the target. Our loss, called Edit-Invariant sequence loss, models the matching of each reference n-gram across all n-grams in a candidate sequence. The design is motivated by the translation invariance properties of ConvNet and captures the edit invariance properties of text n-grams in calculating the loss. Figure 2 shows the invariance property of EISL in comparison with C. We saw this graph. So the loss is increasing at a lower pace than with cross entropy. Uh, figure Appealingly, we show the conventional cross entropy loss in a special is a special case of EISL loss when n equals to the sequence length. EISL calculates the exact sequence matching loss and reduces to cross entropy. Moreover, the computation of EISL is essentially a convolution operation of candidate sequence using target n-grams as kernels, which is easy to implement with existing deep learning libraries. So if you've worked with PyTorch or libraries such as TensorFlow, Keras, then you'll know that they've all have these inbuilt convnets. So you don't really need to bring about any significant like coding work up to implement this stuff. So basically what this saying is, since they've explained the weakness of the cross entropy loss, uh, they want to propose an alternative. So the cross entropy loss certainly has its merits. It is end-to-end differentiable, it's easy to implement and efficient to compute, and which hence can be used as a drop-in replacement or combined with uh, the cross entropy. So the loss is based on the observation that a viable candidate sequence might exist in multiple places. So this translation should not affect the model's certainty of saying that this is a good output, right? So they're basically trying to teach the model to not penalize they're basically not penalizing the model via that loss for such a sentence, and basically then the model will learn that this is also a valid output which I can give. uh, so to demonstrate the effectiveness of EISL loss, we conduct experiments on three representative tasks: machine translation with noisy training target. Noisy training target meaning there are missing tokens or there are extra tokens and so on. Unsupervised textile transfer where only weak forms of references are available, and non-autoregressive generation with flexible generation order. And autoregressive generation is basically what you have with your GPT and BART models, where tokens are predicted one after the other. Non-autoregressive then I guess means that you are not predicting tokens one after the other, and since they're saying there's a flexible generation order, I guess that means to say you can generate in any order. But I'm not really familiar with this type of work, so let's have a look when they explain this. Experiments demonstrate Eisl laws can be easily incorporated with a series of sequence models and outperforms cross entropy and other popular baselines across the board. So you have related works. Deep neural sequence models such as RNNs and transformers have achieved great progress in many text generation tasks like machine translation. These models are typically trained with a maximum likelihood objective, which can lead to suboptimal performance due to cross entropy's exact sequence matching assumption. There are lots of works trying to overcome this weakness. For example, some works propose to use policy gradient or minimize minimum risk training to optimize the expected blue metric. Due to high variance and unstableness in training, a variety of training tricks are used in practice. In the paper by Zhukov and Kretov and Casas et al., they made the initial attempts to develop differentiable blue objectives, making soft approximations to the count of n-grams matching in the original blue formulation. And Zhao et al. Aim to minimize the n-gram difference between the model output and the targets on NAT tasks. Waiting et al. Introduce a new reward function based on semantic similarity for a translation task. So these are all different works, and some of these were discussed in the introduction. Another line of research that is relevant to our work is learning with noisy labels and classification. There are lots of researchers attempting to propose techniques to improve classifier performance in face of noises in labels. For text generation, Nikolai and Silverberg propose student forcing to substitute teacher forcing, which can avoid the influence of noise in target sequence during decoding. So in teacher forcing, I think you give the correct inputs in the RNN generation process. So it has the hidden state, but the lab so the tokens that are going at each time step are the correct tokens, which should have been predicted. So I think this is what that means. But they are using student forcing, which I'm not familiar with. Kang and Hashimoto 2020 proposed loss truncation, which adaptively removed high loss examples considered as invalid data to improve text generation. To the best of our knowledge, our work is the first to investigate sequence training with noisy targets in a principled manner. Alright, so now we have the edit invariant sequence loss. So in this section, we first review the conventional cross entropy loss for sequence learning and point out its weakness, especially when the target sequence is edited. We then introduce the EISL loss, which gives a model the flexibility to learn from subsequences in a target sequence. We first establish notation for the sequence generation setting. Alright, so let x comma y star be a paired data sample where x is the input and y star, where you have the tokens y1 star up to yt star, is the reference target sequence. Further, we define y is y1 all the way up to yt as a candidate sentence. Our goal is to build a model that uh, predicts y given x, that scores a candidate sequence y with a parameter theta. In the sequel, we omit the condition x and the subscript theta for simplicity. So they're saying that when they refer to this in the future, they won't be using theta and x. So they won't be writing this again and again. So this is basically the objective of any text generation model, to have an input and predict the output. So the difficulty of cross entropy loss. The standard approach to learn the sequence model is to minimize the negative log likelihood of the target sequence. So minimize the cross entropy loss. So you basically want to minimize the y star, the negative log likelihood of y star. The cross entropy loss assumes exact matching of a candidate sentence y with the target sequence y star. In other words, it maximizes the probability of only the target y star while penalizing all other sequence outputs that might be close but different with y star. So what this means is basically if you have similar phrases, then the cross entropy model will reward more as compared to if you have more edits than y star. So here if you're getting confused, y star is the target and y is the generated output, I think. The assumption can be problematic in many scenarios. Firstly, for a target sentence, there could be many ways of rephrasing the sentence, such as word reordering, synonym replacement, active to passive rewriting, etc. Many of the paraphrases are viable candidate sequences and/or share many subsequences with the reference sentence, and thus should not be treated completely as negative samples. Similar to the translation invariance which is shown to be effective in image modeling, a sequence loss that is robust to the shift and edits of subsequences in the reference sequence is preferred in order to model the rich variations of sequences. Let me just read that again, this part. So many of the paraphrases are viable candidate sequences and/or share many subsequences with the reference sentence and thus should not be right. So paraphrases should not be treated as negative samples, which are totally wrong. They have some correct aspects to them. Similar to the translation invariance, which is shown to be effective in image modeling, a sequence loss that is robust to these types of shifts and edits in the reference sequence is preferred in order to model the rich variation of sentences, because you have multiple ways of writing the same sentence by making minor variations, which would be penalized by the cross entropy loss. The edit invariance property is particularly desirable when the reference target sentence is corrupted with noise or is only weak sequence supervision. So for instance, in figure 3, the word is repeated twice, which is one of the common errors in typing. Using cross entropy loss, uh, it's on the next page. Using cross entropy loss uh, in the noisy target setting forces the model to learn the data errors as well. So if you have is twice, then the model will learn, okay, this should be correct. It assumes that these are what it should predict. In contrast, a sequence law, less robust or invariant to shift of subsequences, assigns a high probability to the correct sentence even though it does not match the noisy target exactly. The loss thus offers flexibility for the model to select right information for learning. So if the output has one less is, then the EISL would penalize it less than what the cross entropy would, and that would tell the model, okay, this is also a correct way. So you can see a cat is on the red blanket. If you add is twice, then when you match it with the different so this is a noisy target, you match this, so you have a convolution. So you first match it with the first four, then the next four, after one skipping one, then skipping two, and so on. So this is n-gram matching. So this is what their convolutions are. In coordinates, it is essentially the same. You take a filter and then you pass it over the entirety of your image. And you can see here, in some cases it would first be on the circle, then here, then here. So in these cases it would see there is less matching, but in the cases when it totally lies over it or has some partial part over it, then it would have some part of matching. Then let's have a look at EISL, Edit Invariant Sequence Loss. Motivated by the above discussion in this section, we draw inspirations from the convolution operation and enable translation invariance in image modeling, and propose an edit invariant sequence loss. Intuitively, for instance, given a foregram on the red blanket, there is no extra knowledge to determine the position of the foregram in the noisy target sequence. So we compute the losses across all positions in the noisy target sequence and aggregate. This is essentially a convolution over the target noisy sequence with the given n-gram as the convolutional kernel. So this makes sense. We now derive the EISL loss in more detail. So let y a to b be y a to y b minus 1 the tokens between those two positions, and they denote a subsequence of y that starts from index a and ends at index b minus 1, which is of length b minus a. Thus y star I to I plus n denotes the ith n-gram in the reference y star. So because the first n-gram would be 0 to 0 plus n, then the second n-gram would be 1 to 1 plus n, and so on. We denote C y star I to I plus n comma y as the number of times this n-gram occurs in y. So you check if this is equal to the predicted n-gram and the target n-gram if they are equal or not, and you iterate over all the possible I dash values. So you're checking every single I dash, and one dot is the indicator which takes value 1 if the n-gram matches and 0 otherwise. So if there's only one match, then it would be 1. If there are two matches, it would be 2, and so on. So you'll have 1 plus 1, essentially 2. Intuitively, for text generation, we would like to maximize the occurrence of an n-gram from the reference in the target sequence. So for a given probabilistic model, we omit the parameter theta wherever the meaning is clear. The expected value of C can be computed as follows. So since you want to essentially compute this sum, this convolution, which is matching each and every n-gram, the desired n-gram to each and every possible n-gram of the given size. So you can rewrite it as you are basically this is just a way to add a prior, and this is the expectation of y equivalent to py. And so I'm not really sure how I should explain this, but if you're familiar with probability theory, you'll get this part. So I assume you have some familiarity with this, because I can't really explain probability theory right now. That would be way above my pay grade, as well as what I am capable of at this point of time. So thus for the ith n-gram in the reference, a straightforward way to define the learning objective is to maximize the negative log value of its expected occurrence. And so you basically minimize this negative log likelihood of the occurrence of this token between this basically this sum over all the possible convolutions. So you will take y star I to I plus n, you will take this target, and you will match it across y, and the above where y star is the generated and y is the target, I guess. Yep. And y star is the reference, so the desired output, and you iterate over the noisy output in some sense. So you're iterating over the noisy output here. So this summation I dash is over the noisy output, which makes y the noisy output, which means y is the target label and y star is what you generated. The above loss requires computation of the marginal probability of a n-gram, which is interactable in practice with I'm not really sure what interactable means. Does it mean something like difficult to compute, hard to control or deal with? So we therefore derive an upper bound of the loss and use it as a surrogate to be minimized in training. We denote the upper bound as our EISL loss. More specifically, for this loss, you uh, the probability of these being equal is the summation over uh, all these values. Then they say that this loss is upper bounded by this value, and this is what is their loss. So they have the derivation in appendix here. So if you want to go ahead and have a look at it and work it out yourself, then feel free to do so. I won't be doing that in the video right now. Right, so where were we? So notice that the EISL loss involves only the conditional distribution, which is convenient to compute. We first sample the tokens, then compute the negative log likelihood of the reference occurring at position I dash under the model distribution. The full n-gram EISL loss is then defined by averaging over all the positions. And in practice, inspired by the blue metric, we could more straightforwardly combine different n-gram losses depending on tasks. So you could give a weight n to the loss of every n-gram. So you could have a loss of the unigram, a loss of the bigram, a loss of the trigram, and so on. So in this case, this was a loss over the 4-gram, where W1 is the weight of the n-gram loss. The rule of thumb is that a n-gram EISL loss with lower n is more robust to noises, as shown in our experiments. Following blue, we found that simply using equal weights for different n-grams up to n is equal to 4 often produces good performance. As discussed shortly, it is appealing that the n-gram EISL loss is indeed a direct generalization of the cross entropy loss on the n-gram level. So we sum the cross entropy loss of an n-gram over all candidate sequence positions by conditioning a sample from the model. Beside, basically n-gram meaning the entire sentence here. Besides, the derivation of the upper bound makes no assumption on the probability function py, hence holds for both autoregressive and non-autoregressive sequence models as demonstrated in our experiments. So next we have position selection. Minimizing the gram matching loss for over all positions can make the model assign equal probabilities at all positions. Yeah, so which causes the train to collapse. So we further adapt the loss to enable the model to automatically learn the positions of the reference n-grams. For notation simplicity, let GII-n denote the conditional probability that the reference between I and I plus n is equal to the target between I dash and I dash plus n for y less than I dash involved above sequence equation 3. We can vectorize the probability to get this uh, over all the possible GIs, all the possible I dashes basically, since I dash is the one which is varying, I is constant for a given GI, spanning all potential positions of the candidate sequence. We then normalize the probability GIN by Gumbel softmax, denoted by QIN. So they apply the softmax over this vectorized form essentially, which we use as a weight for every n-gram position. So we multiply the weight with the original log likelihood to get the new adjusted loss. The loss can be roughly viewed as the entropy of the unnormalized probability GIN, which has minimal value if the mass of the probability is assigned to one location only. Intuitively, if a GII-n is large, then it is likely I dash is the correct position for the reference n-gram. Hence, the weight for this position should be large. This is like a greedy exploitation in reinforcement learning. On the other hand, to overcome overexploitation, the Gumbel softmax introduces randomness in the weight assignment. The randomness helps balance the exploitation and exploration trade-off in position selection for the model. So Gumbel softmax is just a variation of the softmax. So Gumbel, but I guess it already got it correct. So you have a temperature parameter. Uh, hmm, let's have a look if there's any good visualization which I can use to grasp this a bit better. Uh, right. So let be a categorical vector. The Gumbel, you apply argmax over the one hot encoding, and so I'm not really sure how I can explain this part. I am myself not very familiar with the Gumbel softmax. I've only read about it, but not really seen it in practice. I've just seen papers using the Gumbel softmax trick. So maybe in the future I'll read about it and make a video on it. But right now I won't be able to explain what the Gumbel softmax does exactly. But since it has the word softmax, it would be normalizing the probabilities, and it introduces some form of randomness since it's mentioned here. Let's have a look at efficient computation. EISL as convolution. We show that EISL loss can be computed efficiently using the common convolution operator, which with a very little additional cost compared with the CE loss. In particular, the key quantity log GIN can be obtained as direct output of the convolution operator. To see this, denote V as the vocabulary size. At training, we use random sampling based decoding. That is, for each position I dash, we sample a token Y dash I and feed it to the next step. Denote the corresponding probability output as this pi all the up to t, where pi belongs to rv, is the probability output after softmax at ith position. As shown in figure 4, we can get the loss GIN by applying convolution on log p with yi to I plus n as kernels. So this is, I guess, the Gumbel softmax, since that also had this one hot stuff, or maybe not, where one hot maps each token to the corresponding one hot representation, and convolution is a convolution operation with the first argument as the input and second as a kernel. So this would be the kernel, and this log p is this probability input. We transform p into log domain to turn the probability multiplication into log probability summation. So since in the log domain, when you multiply stuff, it's basically log a, b is log a plus log b, where conv can be directly applied. As shown in figure 4, log p is of the shape v cross t, and one hot this vector is of the shape v cross n. So this convolution is a one dimensional convolution because you will have the same thickness, and the number of columns would just be t and n. So you will have, I guess, t by n or n by t, I guess, n by t number of dimensions in the output, I think. So formally the ith convolution is this formula. After obtaining GIN by convolution, the EISL loss can be easily calculated. So connections with common techniques. A nice property of EISL is that it subsumes the standard CE loss as a special case. So in the case when you have the entire length, it is essentially the cross entropy loss. The connection shows the generality of EISL as a generalization to CE. It enables learning at arbitrary n-gram granularity. So you can see basically what's happening. You are getting kernel operations over, this is the ground truth, and you're doing convolutions over the log probabilities. As a convolution is a common operation for text invariance and image, we adopt a convolution to achieve the translation invariance in text. The input is the distribution from the model output in log domain. Kernel represents the convolution. Kernel and star is the convolution operator. In the 3-gram example, there are 5 kernels, which corresponds to the 5 rows on the right. So it means that you'll have different possibilities. You'll have 5 different kernels which you can make, and for each of them you can create one block. Connections between BLUE and EISL. Both are methods, and the popular BLUE metric uses n-grams as a basis in formulation. Here we articulate the connections and differences between the two. Let us first take a review of the BLUE metric. Specifically, BLUE is defined as weighted geometric mean of n-gram precisions, where BP is a brevity penalty depending on the lengths of y and y dash. N is a maximum n-gram order. Wn are the weights which typically take 1 by n. Precision n is the n-gram precision. Gram n is the set of unique n-gram subsequences of y, and CSY is the number of times a gram occurs, S occurs in y. So this is the BLUE metric. I assume you're familiar with this stuff. The conventional formulation above enumerates over unique n-grams in Y. In contrast, we enumerate over token indexes in calculating the n-gram matching loss. BLUE considers the n-gram precisions and has a penalty term, while EISL simply maximizes the log probability of n-gram matching. The non-differentiability of BLUE makes it harder to optimize. Hence, most prior attempts resort to reinforcement learning algorithms and use BLUE as a reward. But we saw that it causes variance and high variance in gradients and instability during training. There are some works trying to introduce differentiable BLUE metric using approximations. However, such losses are often too complicated and yet to be demonstrated to perform well in practice. So now let's have a look at their experiments. In this section, we present the experimental results on 3 text generation settings: learning from noisy text, and learning from weak sequence supervision, and non-autoregressive generation models. So learning from noisy text. To test the robustness to noise, we evaluate on the task of machine translation with noisy training, in which we train the model with noisy sequence targets and evaluate with clean test data. We test EISL on both multi-30K and WMT18 raw corpus. We use German to English dataset from multi-30K and 29K which contains 29K training instances, as inspired by Shen et al. To simulate various noises in the real data. We introduce 4 types of noises: shuffle, repetition, blank, and the synthetical noise. That is a combination of aforementioned 3 types of noise. The noises are only added to the training target sequence. To verify the validity of EISL on real noisy data, we use German to English dataset from WMT18 raw corpus With this very noisy corpus crawled from the web, we randomly select different number of training samples to test the influence of the data scale. We use transformer-based pre-trained model BART base containing 6 layers in encoder and decoder. We train the model using Adam optimizer with a learning rate of 3 into 10 to the negative 5 with polynomial decay, and the maximum number of tokens is 6000 in one step. The models are trained on a 1 Tesla V100 DGXS with 32 GB memory. We train with CE training using teacher forcing for fast initialization. We then switch to combine 1 2 ngram Eisl with weight 0.8 is to 0.2, meaning 0.8 weight to 1 gram and zero point 0.2 to 2 gram, which we use for the validation using the validation, which we select using the validation set. We adopt greedy decoding in training and beam search in evaluation. We use phasesec to conduct the experiments. We compare Eisl loss with CE loss and policy gradient, where PG is fine-tuned, used to fine-tune the best CE model. Teacher forcing is employed in CE training. We also conduct ablation experiments to explore the effects of different engrams and Eisl loss. We use blue as the automatic evaluation metric for all models. So the results. The results on multi 30K are present in figure 5. The proposed EISL loss provides significant better performance than the CE loss and PG on all PG policy gradient on all noise types, especially on high level noise ends. For synthetic noise as shown in figure 5D, it's interesting to know that CE and PG completely fail where the noise level is beyond 6 in 5D. Yeah, you can see they are totally failing. The blue scale falls sharply, while you can see in these cases the blue scale, the uh, sorry, I was trying to say the blue score falls a bit slowly, but still you can see EISL dominates. uh, the results of different engrams are shown in figure 5e. As the noise increases, the importance of lower engrams is more obvious since you want the single tokens to be correct. The results on real noisy data WMT18. So you can see as the noise is increasing, the 1 grams are having the best blue scores. You can see they are on the top, the orange ones. So this is on the WMT18. EISL loss achieves better performance than CE and PG, and the difference is getting larger when the training data increases. This again demonstrates EISL could learn more valid information in rather noisy data, while CE loss, which only demonstrates whole sequence matching, could struggle on noisy data. So learning from weak supervision style transfer, we experiment on different type of style transformations, sentiment and political slant to verify EISL can learn from weak sequence supervision. So they use a standard Yelp review dataset and political dataset. Yelp almost contains 250k negative and 380k positive sentences. That ratio for training, valid, and test is 7:1:2. Lee et al. Annotated 1000 sentences as ground truth for better evaluation. The political dataset is comprised of two-level comments on Facebook with 412 members of the US Senate and House who have public Facebook pages. The dataset contains 270k Democratic and 270k Republican sentences. There exists no ground truth for evaluation. The data pre-processing follows this paper Tian et al. Uh, the structured content preservation model is adopted as the base model. We use the Adam optimizer, batch size 128, model is trained on Tesla V100 DGXS 32 GB. We compare the results between the base model and the model trained with EISL. Specifically on top of the base model, we add the EISL loss, a combination of 2, 3 and 4 gram with the same weight, so 0.33, to reduce the discrepancy between the transferred sentences generated by the language model and the original sentence. We assign EISL loss with weight 0.5. Following previous work, we compute automatic evaluation metrics, accuracy, blue score, perplexity, and pause distance. For accuracy, we adopt a CNN-based classifier trained on the same training data to evaluate whether the generated sentence possesses a target style. So remember, this is a text style transfer problem. Then we measure blue score and blue human score of transferred sentences against the original and ground truth being the one labeled by Lee et al. PPL metric is evaluated by GPT-2. PPL is perplexity. After fine-tuning on the corresponding dataset with the goal to assess the fluency of the generated sentence, pause distance is used to measure the model's semantic preservation ability. We also perform human evaluations or Yelp to further test the transfer quality. We first randomly select 200 sentences, generate the output. Then for each original sentence, we present the outputs of the base model and ours in random order. The three annotators are asked to evaluate which sentence is transferred as the transferred sentence of the original sentence in terms of content and sentiment. They can choose either option or select the same quality. We measure the percentage of times each model outperforms the other. So the result, as sentiment results show, the blue gets improved from 65.71 to 68.51 with EISL loss on the premise of the correctness of sentiment transfer. EISL loss plays a critical role to guarantee lexical preservation, and meanwhile all of blue, PPL and pause distance get improved. It is not surprising that EISL loss helps generate sentences more fluently and select the more appropriate words condition on the content information. As the human evaluation results are shown in Table 1, the model with EISL loss performs better in accordance to automatic metrics. After analyzing the generated samples, we found EISL loss could drive the model to adopt the words which fit the scene better and understand more semantics, but not just replace some keywords. So you can see the examples and results in appendix. Our model outperforms all models on blue, PPL, and pause distance with comparable accuracy. For a more fair comparison with the base model, our EISL loss improves the base on all four metrics, including the accuracy. The above result demonstrates the effectiveness of our EISL for weak supervision tasks, which could improve not only transfer accuracy but fluency and content preservation. So they mentioned this table. You can see with EISL they are outperforming everything except for perplexity. Perplexity, the lower the better, is still with he et al. So I guess maybe if they incorporated, they worked more on sort of improving, using a more better or advanced model, they could have even better results, I guess. I'm not really sure about that part, but still it outperforms in a lot of things. So Tian et al. With the blue score is with the EISL loss is this last row, and this is the percentage of human evaluation. So the result denote the percentage of input for which the model has better transferred sentence than the other model. So with EISL, 30.7% of the time it has better, and equal it has 47.3% times equal. As sentiment results are shown in table 1, we saw this already. Uh, Table 2 is for the non-autoregressive. So let's see how much. Oh, we are already at the end. So learning non-autoregressive generation. Non-autoregressive neural machine translation, NAT for short, is proposed to predict tokens simultaneously in a single decoding step, which aims at reducing the inference latency. The non-autoregressive nature makes it extremely hard for models to keep the order of the words in the sentence. Hence, cross-entropy often struggles with NAT problems. In experiments, we show EISL is superior to CE in NAT, which requires modeling flexible generation order of the text. They again use the English to German WMT14, which contains 4.5 million training instances. We tested our proposed EISL loss on both fully NAT model with the vanilla NAT and the NAT CRF, and iterative NAT model INAT, LEVT, and CMLM. We also compare with some strong baselines in Appendix 8.2.2. They use Adam, inverse square root scheduler. We apply sequence level knowledge distillation to the dataset, which can reduce the complexity of the dataset, making it easier for the model to learn and improve the performance. The models are first trained by cross entropy for fast initialization, then focus on 2 gram, 3 gram, 4 gram with the same weights, so 1 by 3 each. FAIRSEC is adopted to conduct the experiments. We average the last 5 checkpoints as the final model. So you can see here with EISL, all the models are better, clearly. Incorporating EISL enhances the performance, and quite not what the autoregressive models are, since you're still you don't have like the text generation, so the sequencing is not the problem of the loss function. It's how the problem is, since you're not predicting tokens one by one, then ordering is of course going to cause problem. But you can see the jumps, right? uh, Iterative that could run in say, multiple decoding iteration. However, the first decoding iteration of the model is fully non-autoregressive, which is what they use as a baseline. So in the autoregressive, in the iterative ones, they use only the first iteration. Results: we first summarize the comparison with EISL and CE loss in Table 2. The proposed EISL can improve the model performance. For fully NAT model, EISL can improve directly. For iterative NAT models, if we restrict the iteration step to a small level, EISL can significantly outperform the baseline. And with increasing of iteration step, the difference fades away. However, as studied in Kasai et al. 2020, iterative NAT models do not hold the intrinsic advantage of speed while using many decoding iterations and transformer baselines with a shallow decoder can achieve comparable speedup and only at a significant sacrifice a minor performance drop. Further, we compare the performance of CMLM and EISL against 5 baselines in the appendix, showing the superiority of EISL loss. Therefore, comparing the CE loss and other strong baselines, EISL possesses great generation capacity. Conclusion: we achieved an edit invariant sequence loss for end-to-end training of neural text generation models. The proposed method is insensitive to the shift of n-grams in the target sequences, hence suitable for training with noisy data and weak supervision, where CE loss fails easily. We show CE loss is a special case of EISL and build a connection of EISL with blue metric and convolution operation, which both have the invariant property. Experiments on translation with noisy target textile transfer and non-autoregressive neural machine translation demonstrate the superiority of our method. We are excited to explore more applications of new loss function on different problems. So they've clearly showcased their model. The loss function works and enhances the outputs. Overall, the paper was a pretty good read, and even though it got math heavy at times, I could follow along even if I could not understand. I did not know some parts, but the intuition helped. They also have some more results here which you can have a look at. I'm not going to have a look at in the video, but they essentially graphs and more results with comparison to other things. So thank you guys for tuning in. If you have any more papers which you want me to cover and I might find them interesting, then do comment them down below. As always, please like, share and subscribe, and hope to see you again next time.